This PowerPoint is on fluids. So first off, we start with states of matter. We got solids, liquids, and gases. Now the important thing about this is that we see that solids are going to have a constant volume and constant shape, while liquids will have a constant volume with a changing shape, and then gases have a changing volume and changing shape. Now the reason I bring this up is because liquids and gases are both considered what we call fluids. So fluids are anything that don't have a fixed shape, which you can see here is going to be liquids and gases, and they can flow, so they can move from one place to another just by pouring. Now an ideal fluid is incompressible. And what that means is if you add pressure to it or you push on it, then it's not going to change its volume. And then no viscosity. So clearly a lot of all liquids have viscosity, some sort of viscosity, and that's some like bond attachment to things they stick to. Kind of like if you just put water on your hands and then you try to shake them off, you still have some water on your hands because it's kind of grasping to your hands. It doesn't just all fall off. Now gases are not ideal. They are compressible, but there's a lot of things that we can talk about with fluids that can translate over to gases. The principle, the idea is still there, even though it may not be a perfect translation over. So density is a concentration of mass per unit of volume. So we use the density is going to be a letter rho. It's a Greek letter rho, and it's going to be mass over volume, which is measured in kilograms per meters cubed. Now, if you use density in chemistry, usually it's going to be grams per centimeter cubed, but in physics, base units is going to be kilograms and meters. So the volume of is found by a variety of methods. We've got a few things that a few shapes that we use to find volume: length times width times height. It's for a cube. A sphere is 4/3 pi r cubed, and then a cylinder is going to be pi r squared, which is the area of the base, and then times the height. And then one of the major constants that we use, water, is going to be 1,000 kilograms meters cubed. We're going to be using that a lot in a lot of our equations and problems in physics. So pressure itself is the force that the molecules of a fluid, basically when they collide with the sides of a container. So you can see here like one particle hitting and then bouncing back. There's basically a force in the horizontal direction, and that force, that is the pressure that the container is pushing on the particle with. So the more surface area that you have, the more collisions you're going to have, which increases your pressure. Average pressure is going to be force divided by area. Force is measured in newtons, and then area is going to be in meters squared, and newtons per meter squared is now going to be a new unit that we call a Pascal. Atmospheric pressure itself is going to be essentially the weight of the atmosphere, not the weight of the entire atmosphere of the entire Earth. It's basically the weight of the atmosphere directly above you as it's pushing down, and it's holding the Earth's gravity is holding onto that on its surface that's pushing against you. The air molecules that collide with you, they create the pressure on your body. 1 atmosphere. So we have some standard units that we talk about. Pascal is base units. It's going to be 1 atmosphere is actually 101.5 kilopascals, but we go ahead and just round that to 1 times 10 to the 5th pascals, and then 14.7 pounds per square inch. So if you took your body, for example, that has about 1.7 square meters of surface area, then this is 170,000 newtons, which is 38,000 pounds, about 19 tons of force that is acting on you. Now, the reason it doesn't actually crush you is because the inside of your body has compensated for that over the years of living on Earth and having that inward pressure inside your body pushing out with as much pressure that the outside is pushing in. So the next thing we talk about is Pascal's principle. Basically, example here, this is referred to as basics of hydraulics. So we have a small surface area over here that a force is being applied. How does that translate over here? So because the liquid itself, or the fluid, is not compressible, then that means the change in pressure on this side will translate through the entire fluid and cause a change in pressure on that side. And since pressure is force divided by area, then you can see here a small force with a small area has the same ratio as a large force over a large area. So apply a small force over a small area over here. That translates over to a larger force for a larger area, cross-sectional area here. So if we rearrange this equation, we could see that the force that's being applied on this side is going to be equal to the force on the other side times the ratio of the areas between the two forces and where the forces are being applied. Now, just to kind of show why this principle works, I'm going to take this equation and show you that actually the work being done, force times displacement, the work being done is going to be the same on this side as it is over here. So essentially this is a conservation of energy effectively. The work done over here is equal to the work done over there. So let's say this force 1 pushes down a distance of d1 and the truck raises up d2 with a force of F2. So if you look at your work is the work I do on this side. That's going to be equal to your force 2 times area 1 over area 2 times distance 1. Now you can see that area 1 and distance 1, so the cross-sectional area and the distance that it moves down, that is going to be a volume, and that volume transfers over. And since it's incompressible, then the volume that transfers from here goes over there as well. So then those volumes are going to be equal to each other. So the volume change on this side and the volume change on this side are going to be equal. So volume 1 equals volume 2. And then when we plug that in here, we can see that the cross-sectional area here gets canceled, and I get the force over here, and the distance that it's pushed is going to be multiplied together, and that gives me the work on this side. So that's how we show that the work done over here on this side with this force is going to be equal to the work done over here. The difference though is that the force that's being done over here is done over a large distance. So a small force over a large distance gives you a large force over a small distance. This example, it says 2 identical containers are filled with water. The first is completely full and the second one is only half full. Which has more pressure? So we have this that has more material, more liquid in there than this. So that would make sense that if we talk about pressure being the weight of the material as it pushes down on the bottom of the container, then this having more material should have more weight, and therefore the pressure in 1 will be greater than the pressure in 2. So how much pressure is on the bottom of the container? So if we include the atmospheric pressure that's pushing on it, so that the liquid that's in here as well as the effectively all the air above is going to push down so that we have a total pressure on the bottom. So the pressure from the water is going to be the force of gravity of the water divided by area, and then the pressure of the atmosphere is going to be added to that to get the total pressure on the bottom here. Now force of gravity, that's going to be equal to mass times the acceleration due to gravity, and the volume here we know is going to be the cross-sectional area times the height. So if we take that force being mass times gravity, and then we're going to multiply both the top and the bottom by height, and you'll see why in a second, because the denominator here is going to be equal to the volume of the liquid, and taking that volume in the denominator and mass in the numerator, that's where we get density. So density is going to be equal to mass divided by volume, which is that part right there, and then the density times the acceleration due to gravity times the height that's going to give us a pressure that the water pushes on the bottom of the container, and then we have the atmosphere also pushing on it. So those two together will give you the total pressure at the bottom of this container. So the absolute pressure is going to be the atmospheric pressure plus the effectively the weight of the water itself. So the weight of the atmosphere and the weight of the water combined to give the total weight being pushed on the bottom. Now, if we take the difference between the atmospheric pressure and the absolute pressure, that's what we call gauge pressure. Gauge pressure is effectively just the weight, the pressure just due to the liquid itself. So here we have 2 dams of equal height prevent water from entering the basin. You can see that A is going to have a very, very thin amount, and then B has a very thick amount, but the height and the area, the cross-sectional area of the dam itself is going to be the same. So the question here is which one has more force on this wall that's holding back the water? And the answer is that they're actually going to have the same force, that the amount of liquid it has behind it is not really that doesn't really affect how much force this is being applied. Really, the only thing that affects how much force is being applied is how deep that wall is, that amount of water that's on there. So you can see that the pressure is due to the density times gravity times height. That is going to be essentially the only thing that affects how much pressure and how much force the dam is holding back on the water. So if we look at if you've ever seen a water mill or a water tower, this water tower, you can see that there are bands at the bottom that are closer together than the bands at the top. Now the reason for that is because as you get higher up, you get less pressure. That's from this equation right here, density times gravity times height. So because the height is from the surface of the water the surface of the water is at the top here. As you go down, you get more pressure as you go down, which is why these bands are closer together. You need more support at the bottom in order to keep that water tower contained. The next topic I want to talk about here is the pressure and depth created with barometers. So looking at this barometer, effectively what we have is we have the atmosphere that's pushing on top, but you can see that the liquid is continuous in here. So none of the air here is getting inside, and this space at the top here is going to be empty. No air, no liquid, nothing in there at all. Essentially, that's what we call a vacuum. So if this is not moving, then there is going to be pressure that's going to be pushing. That pressure here is pushing the liquid up, since there's no pressure at the top that's pushing it back down. So to figure out that, we have the pressure 2 is going to be equal to pressure 1 plus the basically the weight of the liquid itself. Pressure 2 is going to be the atmosphere. Pressure 1 is going to be 0. Those are going to be not going to be the same. So this is our gauge pressure, but we don't have any pressure on the inside there. So effectively we have the density of the liquid times gravity times height, and that'll tell us effectively how much atmospheric pressure it is. So if you look at the density and gravity and height and multiply those together, we can figure out atmospheric pressure. That's what a barometer does. Now a barometer uses mercury. The reason why we use mercury is because mercury is so dense as compared to a lot of other liquids that it doesn't need to go very high to indicate how much pressure is there. So looking at the density of mercury, it's going to be 1.36 times 10 to the 4th kilograms per meter cubed. That's about 13.6 times what water is, which means it takes water 13.6 more grams or more kilograms in order to equal the same volume as 1 kilogram of mercury. And then the atmospheric pressure, as we said before, is 1.0 times 10 to the 5th. So using this equation, we go ahead and figure out what the height would be of this column in order to show how much pressure is being pushed on it. So in solving that height, we get about 0.750 meters of mercury, or 750 millimeters of mercury, which converted over to inches is about 29.5 inches of mercury, which is what we consider 1 atmosphere. So if you ever see pressure measured in millimeters of mercury, this is why. This is a barometer that the atmosphere pushes down and then pushes that up into a certain column, that the height of that column tells us how much pressure. So a higher height would be more pressure, a lower height would be less pressure. So our question here, it says, is it possible to stand on the roof of a 5-story building, which is about 15 meters, and drink using a straw from a glass on the ground? Now, there's a misconception with straws, and that is that when you suck in a straw, you're actually pulling the liquid towards you, and you're actually not pulling the liquid. What you're doing is effectively creating a barometer where you're reducing the air that's above the liquid, and that air is then creating that vacuum. Then the outside atmosphere is what pushes the liquid up. So you're actually not doing anything here. You're just removing the air when you pull in with your lungs, and then that the atmospheric pressure pushes up there. So looking at this equation, if we look at water, the density of water is going to be 1,000. The acceleration due to gravity is going to be 9.8. So when we divide the atmospheric pressure by those two values, we're going to get that the height of the water that it can go is going to be 10.2 meters. So if you remove all of the air above inside that straw, then the liquid can only go up 10.2 meters. And because that is less than the height of the 5-story building, then that means that no, you're not going to be able to actually drink through a straw at 15 meters up, because the water itself, the atmosphere, will not be able to push it up that high.